In 1927, a physicist named Werner Heisenberg made a discovery so disturbing, so fundamentally threatening to everything we thought we knew about reality, that he reportedly sat up all night after the experiment, alone in his lab, shaking, not from cold, not from fear, but because he had just proven that the universe, the entire universe, does not fully exist until something is watching it. And here's what nobody tells you. The experiment that proved this has been replicated hundreds of times. It works every single time, and physicists still can't explain it. If you're new here, this channel goes to the most extreme, most disturbing corners of science every single day. Subscribe right now and hit the bell. New video drops tomorrow, and trust me, you don't want to miss it. Now, let's talk about the experiment that broke reality. Before we get to the experiment that shook Heisenberg to his core, we need to understand something basic, something you already know. You just don't know you know it. Drop a stone into still water. What do you see? Ripples, waves, spreading outward in concentric circles from where the stone hit. Now, drop two stones at the same time. Two different spots. Watch what happens where the ripples meet. In some places, the waves crash together and create a bigger wave. We call that constructive interference. In other places, the peak of one wave meets the trough of another, and they cancel each other out. Perfectly flat water where two waves collided. We call that destructive interference. This is the key to everything that follows. Remember it. Constructive interference. Waves add together. Destructive interference. Waves cancel each other. Now, 1801. A physicist named Thomas Young set up a simple experiment. He took a barrier with two thin slits cut into it. He shone a beam of light through those two slits onto a screen behind. If light were made of particles, like tiny bullets, you'd expect to see two bright lines on the screen, one for each slit. Particle goes through slit 1, lands on the screen. Particle goes through slit 2, lands on the screen. Simple. But that's not what Young saw. He saw a pattern of dozens of alternating light and dark bands on the screen. An interference pattern. The same pattern you get when two waves in water collide, which meant light wasn't behaving like a particle, it was behaving like a wave, spreading out through both slits simultaneously, interfering with itself, creating peaks and troughs of light. Okay, mind mildly blown, but this is the 1800s. Fine, light is a wave, we can handle that. Then Einstein came along and ruined everything. 1905, Albert Einstein, working on something called the photoelectric effect, proved that light is not just a wave, it's also made of individual particles, packets of energy, discrete indivisible units. He called them photons. He won the Nobel Prize for it. Not for relativity, for photons. And that created a problem, because Young had already proved light was a wave, and Einstein had just proved light was a particle. Both experiments were correct. Both results were reproducible. Both could not simultaneously be true, and yet they were. Light, it turned out, is both a wave and a particle, depending on the situation. Physicists called it wave-particles duality, which is a very calm, professional name for something that should have caused a complete breakdown of scientific sanity. But here's where it gets truly catastrophically strange, because once we had the technology to fire light one photon at a time, scientists decided to repeat Young's double-slit experiment, but firing individual photons through it, one at a time. If a photon is a particle, a single discrete object, then it can only go through one slit, left or right. It's not a wave anymore, it's a bullet. It has to pick a side. So you'd expect, over time, as you fire thousands of individual photons, you'd build up two lines on the screen, one for each slit, like two stacks of bullet holes. That's what should happen. That is not what happened. When scientists fired individual photons through the double slit, one at a time, each photon landed on the screen in a seemingly random spot. But as thousands of photons accumulated, the pattern they formed was an interference pattern. The same wave interference pattern Young saw in 1801, which is impossible because a single photon, fired alone with no other photons present, somehow went through both slits simultaneously, interfered with itself, and landed exactly where the mathematics of wave interference predicted it would. The photon, a single individual particle, behaved like a wave spread across the entire experiment, as if it existed in multiple places at once. Physicists had a name for this. They called it superposition. The photon doesn't take one path, it takes all possible paths simultaneously. It exists as a mathematical wave of probabilities, not in one place, but smeared across every possible location it could be, until it hits the screen, and then, only then, it becomes a single particle in a single location. Strange, deeply strange, but maybe still manageable. Then someone asked the obvious question: if we put a detector at the slits, just to watch, to see which slit each photon actually goes through, what happens? And this is the moment Werner Heisenberg sat alone in his lab, shaking, because the answer was this: the moment you observe which slit the photon goes through, the interference pattern disappears, gone, completely gone. Instead, two lines, exactly what you'd expect from particles. The photon, the moment it is observed, stops behaving like a wave. It stops being in superposition. It picks a side. It becomes a particle, as if it knew it was being watched and behaved differently because of it. This is the observer effect, and what it means is the most disturbing thing in the history of science. Let's be very clear about what just happened in that experiment. The photon, when unobserved, existed as a wave of possibilities. It was everywhere and nowhere. It had no definite position, no definite path. It was pure potential. The moment it was observed, the moment a detector tried to measure it, it collapsed into one specific, definite position, one reality, out of infinite possibilities, caused by the act of observation. Now, popular science will tell you that this is just because the detector interferes with the photon, that we're disturbing the system by measuring it, that it's a mechanical effect, not a philosophical one. And that's partially true. But here's what popular science doesn't tell you. In 1978, physicist John Wheeler proposed an experiment called the delayed choice experiment, and it is significantly more disturbing. Here's the setup. Wheeler asked, what if we wait until after the photon has already passed through the slits, and then decide whether to observe it? Can a decision made after an event change what happened during the event? The answer, confirmed experimentally in 1984 and again in 2007, is yes. When scientists chose to observe the photon after it had already passed through the slits, it retroactively behaved like a particle, as if it had always picked one slit, even though no measurement was made while it was passing through. When it chose not to observe it after it passed, it had formed an interference pattern, as if it had always gone through both slits simultaneously. The photon's past behavior, which slit it went through, was determined by a decision made in the future. Observation, it seems, doesn't just affect the present, it affects the past. Let that sit for a moment. If the act of observation changes the behavior of particles, and that change can reach backwards in time, then what was the universe doing before there was anything in it capable of observation? Before there were eyes, before there were brains, before there was life of any kind? Was the universe, was all of space and time and matter just a wave of possibilities, pure potential, existing in superposition everywhere and nowhere, waiting? Physicist John Wheeler thought the answer was yes, and he had a name for his theory. He called it the participatory universe. Wheeler's idea, the participatory universe, is one of the most radical proposals in the history of physics and one of the least talked about. The idea goes like this: the universe does not simply exist, with observers passively watching it from the inside. Instead, observers are required for the universe to exist at all. We, conscious beings capable of observation, are not just passengers on a rock flying through space. We are, in some deeply fundamental physical sense, participants in the creation of reality. Every time you look at a star, the act of looking collapses its quantum wave function. You are participating in defining its reality. Every time a measurement is made anywhere in the universe, reality is being crystallized from possibility. Wheeler believed that without observers, the universe would remain in superposition indefinitely, not existing, not existing, just potential. And here's where it connects to something much bigger. If observers are required for physical reality to crystallize from quantum possibility, then the universe, a 13.8 billion-year-old universe that existed for billions of years before any conscious life evolved, either had some form of observer from the very beginning, or the universe somehow knew in advance that observers would eventually arise and waited. Or, and this is the option physicists are most reluctant to say out loud, the universe created the conditions for conscious observers on purpose because it needed them. This sounds like philosophy. It is, in fact, an active area of theoretical physics, and it has a direct, immediate, disturbing implication for the search for alien life. Here is something almost nobody puts together: the observer effect, the participatory universe, and the Fermi paradox are three separate ideas that, when you combine them, point to something extraordinary. The Fermi paradox asks, if the universe is so vast, so old, so full of stars and planets, where is everyone? Where is the alien life? The standard answer is, we don't know. Maybe they're too far away. Maybe they haven't evolved yet. Maybe they destroy themselves. But Wheeler's participatory universe offers a completely different answer. If observers are fundamental to physical reality, if consciousness plays an actual role in collapsing quantum possibility into physical existence, then the universe has a vested interest in producing observers. Conscious life is not a cosmic accident. It is a cosmic necessity. The universe requires observers the way a fire requires oxygen, not metaphorically, physically. And if that's true, if the universe is fundamentally oriented toward producing a consciousness, Then the Fermi paradox stops being a mystery about silence and starts being a question about timing. Maybe we are early, maybe intelligent. Observing life is still rare, still bootstrapping itself into existence across the cosmos. And we are among the first. The universe, 13.8 billion years old, enormous beyond comprehension, spent most of its existence as a dark, cooling gas cloud. Stars had to form, then die, then reform with heavier elements. Then planets had to cool. Then chemistry had to find the right configuration. Then biology, then neurons, then consciousness. 13.8 billion years to produce a creature capable of pointing a telescope at the sky. We may not be alone, but we may be early. And if we are early, if humanity is among the first observers in a universe that fundamentally needs observers, then what we do next matters in a way that goes far beyond politics or economics or survival. We are the universe becoming aware of itself, and we have barely begun. Werner Heisenberg sat alone in his lab in 1927. He had just run the numbers on the uncertainty principle, the mathematical proof that observation affects reality at the quantum level. And he wrote in his notes that night, I repeated to myself again and again the question, can nature possibly be as absurd as it seemed in these atomic experiments? He never fully resolved it. Neither have we. The observer effect has been confirmed hundreds of times. The delayed choice experiment has been confirmed. The mathematics work. The predictions are accurate. But the meaning, the reason why observation affects physical reality is still, after 100 years, unknown. Physicists have interpretations. The Copenhagen interpretation, the many worlds interpretation, Wheeler's participatory universe, quantum consciousness theories. None of them are universally agreed upon. All of them are deeply, fundamentally strange, and all of them point to the same conclusion. The universe is not what you think it is. Reality is not a solid, fixed, external thing you are moving through. It is something that is, in some way, we don't yet understand, shaped by the act of being experienced. You are not just in the universe. The universe, in some sense, may be in you. I want to know what you think about this. Do you believe consciousness plays a physical role in the universe, or is the observer effect purely mechanical? Drop your answer in the comments. One word, either mechanical, if you think it's just physics with no deeper meaning, or participatory, if you think Wheeler was drawn to something. I read every single comment, especially on videos like this one. Tomorrow on Decode Deep Space, we're gonna talk about a planet that used to exist in our solar system, one that disappeared, and what scientists believe caused it to vanish, changes everything we thought we knew about how our solar system, and by extension, how Earth itself, came to be. That video drops tomorrow. Subscribe, hit the bell. I'll see you then. We're just getting started.